Welcome to this beginner-friendly guide on C-Sharp AI logic, where we'll unlock the secrets to creating intelligent game characters. Game AI is crucial for immersive experiences, making virtual worlds feel alive and challenging for players. Today, we'll explore three fundamental techniques: finite state machines, behavior trees, and pathfinding. These powerful concepts are essential for developing sophisticated AI behaviors, all implemented using C-Sharp. First, let's dive into finite state machines, or FSMs, a powerful concept for managing AI behavior. An FSM defines an entity's behavior through a finite number of distinct states. Transitions between these states occur based on specific conditions being met. Consider a simple enemy AI. It can be in states like idle, patrol, chase, or attack. When a player enters its site, the AI transitions from patrol to chase. If the player escapes, it might transition back to patrol or even idle. Here's a basic C-sharp implementation structure for our enemy FSM, starting with an enum for states. We'll use a current state variable to track the AI's active behavior. A update state method will be called every frame to process the current state's logic. Inside update state, a switch statement handles the logic for each specific state. Each case within the switch statement contains the unique actions and transition checks for that state. To transition, we simply update the current state variable to the new desired state. A helpful tip: avoid creating FSMs with too many states and transitions. Overly complex FSMs can become difficult to debug and maintain as your AI grows. Next, let's explore behavior trees, a more scalable alternative for complex AI. Behavior trees organize AI logic hierarchically, allowing for modular and reusable behaviors. They execute tasks by traversing a tree structure, evaluating nodes from top to bottom. The main node types are sequence, selector, decorator, and leaf nodes. Sequence nodes execute their children in order, succeeding only if all children succeed. Selector nodes try their children in order, succeeding if any child succeeds, and stopping there. Decorator nodes modify a single child's behavior, such as inverting its success or repeating it. Leaf nodes are the actual actions or conditions, like move to target or is player visible. Here's how a behavior tree might structure our enemy AI, making it more modular and readable. A basic C-sharp code structure for implementing a behavior tree involves defining a base node class. Derived classes like sequence node, selector node, and action node inherit from this base. Each node has an execute method that returns its status: running, success, or failure. This status determines how the parent node continues its execution flow. Tip: choose behavior trees over FSMs when your AI needs complex, dynamic, and easily extensible behaviors. BTs excel in scenarios where AI needs to react to many different situations with varying priorities. Finally, let's explore pathfinding, essential for intelligent AI movement in any game. Pathfinding allows AI to navigate complex environments, avoiding obstacles and reaching destinations efficiently. The A** algorithm is a popular and efficient choice for finding the shortest path. A** works by evaluating nodes on a grid, considering movement cost from the start, known as G. It also estimates the distance to the target, called the heuristic or H. The total cost, F, is the sum of G and H, guiding the algorithm to the optimal path. A** uses an open list of nodes to be evaluated and a closed list of nodes already visited. It continuously selects the node with the lowest F cost from the open list. Here's a simplified C-sharp code example for implementing the A** algorithm. Our node class will store its grid position, parent node, and the G, H, and F costs. The findPath method takes a start and end position, returning a list of nodes forming the path. The core logic involves iterating through neighbors of the current node. For each neighbor, we calculate its G, H, and F costs. If a better path to a neighbor is found, its costs and parent are updated. Finally, the neighbor is added to the open list if it's not already there. A crucial tip for performance: implement pathfinding on a separate thread. This prevents the main game loop from freezing during intensive path calculations. Alternatively, use techniques like hierarchical pathfinding for very large maps. We've covered finite state machines for clear, defined behaviors, behavior trees for modular and scalable AI, and A** pathfinding for efficient navigation. These three techniques form the bedrock of intelligent game AI. Combining them allows you to create truly dynamic and intelligent AI for your C# games. For example, an FSM could manage high-level states, while a BT handles complex decision-making within a state. Pathfinding then provides the movement capabilities for these behaviors. Keep practicing, experiment with different scenarios, and continue building amazing game AI. Your journey into C# AI development has just begun. Happy coding!